what about other titrations? So we could do a weak base getting titrated with a strong acid. So we could start off with like ammonia and titrate it with hydrochloric acid. And it's going to have a similar process to solving all the points on this titration curve, like we would for the weak acid being titrated with the strong base. It kind of looks like a flipped upside down version of that, where we're starting off high, we've got it kind of flat for a while, and then it goes low. But like, let's take a look at it. So in the beginning, we've got 0.1 molar ammonia, right? I'm going to treat this just like I would a weak base problem, where my concentration of hydroxide is going to be the square root of Kb times the initial concentration. Again, we're going to assume that they're well separated from each other. So I just have the pH for the weak base. Right? It's going to then enter a buffer region as we add in the strong acid. So the H3O plus is going to react with the ammonia to form ammonium, the conjugate weak acid, and water. So along here I've got a mixture of ammonia and ammonium. I can do Henderson-Hasselbalch, but at halfway to the equivalence point, pH is going to be equal to pKa. Right? So I want to take my Kb, turn it into a Ka. That's still going to work. pH equals pKa. As I keep going and I add more, I'm going to reach the equivalence point. I will have added in an equal number of moles of titrant and to the titrate. Right? So the number of moles of H3O plus added are equal to the moles of NH4 plus that I started with. And at this point, I've reached the equivalence point. You notice that this transition is happening over a range of about 4 to 6. Right? So phenolphthalein will not work for this titration, but methyl red will. And again, notice it's a very narrow range over which that large pH jump happens. So this is like maybe 40.1 milliliters and 39 milliliters. Not a big change, but resulting in a large pH difference. At this point, we can use our shortcut that says that the pH is equal to here our H plus ion concentration is going to be the square root of Ka times the new volume, the concentration adjusted for the new volume, because remember we've added in some extra volume here of titrant. And then again, that's also assuming that our separation between K and C are good. Beyond that point, all right, we've added in 1 drop extra. Now we've got excess H3O plus. It's going to work like a strong acid problem, and the volume needs to be corrected for. Again, I would go out all the way to an extra twice the equivalence volume, because then the moles of H3O plus are going to be equal to the moles of my starting titrant. It just makes the math a little bit easier. So in summary, for a titration of a weak base with a strong acid at 0, I've got no added acid. It's just a weak base in solution. Use the weak base dissociation equilibrium equation, the ice table, and Kb to calculate the hydroxide ion concentration. Convert that to a pOH and then a pH. Between 0 and the equivalence point, the solution is a buffer, right, except for the bendy parts. So the flat parts, it's a buffer. It's a mixture of the base and its conjugate acid, weak base and its conjugate acid. Use the reaction stoichiometry to calculate the moles of the conjugate acid and the conjugate base. After the strong acid converts some of the conjugate base into the conjugate acid. Use the Henderson-Hasselbalch equation to calculate pH, or you go for the easy one where you've got half the equivalence volume and pH equals pKa. Right. At the equivalence point, the only solute that's going to affect the pH is going to be that salt. So it's going to be the conjugate weak acid from my conjugate weak base. So it's going to be the conjugate acid. So it's going to be the HA is the only thing in there. It's going to be weakly acidic. pH isn't 7. You need to calculate it. The molarity of do that by using the molarity of HA by the moles in the total volume. Do an ice table, obtain H plus, and convert to pH. Beyond the equivalence point, you've got excess H plus. Lets you determine H plus ion concentration. You've got some H plus from the weak acid dissociating, but it's minimal and you can neglect that. Use reaction stoichiometry. The reaction stoichiometry to calculate the moles of excess H plus. calculate the total volume, calculate the molarity as moles divided by volume, convert it H plus to pH. Right, so let's look at a comparison of the different types of titration curves, right? So if I've got a strong acid and a strong base, well, this is a strong acid being titrated with a strong base. It's nice and sharp. The weak acid looks similar in the right-hand half to the strong acid, strong base, but it's got this buffer region in here. Here on the strong acid, the equivalence point is going to be 7. Afterwards, it's dominated by OH. Before, it's going to be the excess H3O+. Right here in this part, it's the same part for the base part after we've reached the equivalence point, but the equivalence point is going to be a conjugate weak base. So it's going to be up above 7. Along here, it's a buffer. And then there it's the weak acid. For the weak base being titrated with a strong acid, it's going to look like a flipped upside down version of this. I'm going to start off basic. It's going to have this little divot here where we cannot use the Henderson-Hasselbalch. We'd have to use the full-on ice table. It's got the buffer region in here, and then it takes a sharp dive down. Once we've reached the equivalence point is below 7 because all I've got in solution is a conjugate weak acid, and then it flattens out when I've got just excess H3O+, controlling the pH. What if I've got a polyprotic acid? Well, a polyprotic acid is going to have more than one Ka, and there's going to therefore be 2 equivalence points in the titration. Right? So this is or more, depending on how many removable protons we've got. The closer the Kas are to each other, the less distinguishable those equivalence points are. But they're going to happen at the same number of added milliliters of titrant. Right, so it's going to take me 25 milliliters to reach the first one, and it's going to take me 25 milliliters to reach the second one. If it was triprotic, there'd be a third bump over here, third titration break at an additional 25 milliliters. So these guys are going to be evenly spaced. It's just that because the Ka might be small, remember what we said about Ka? The smaller they are, the smaller this hump is. So that second Ka might have a very, very small bump to it. It might be hard to see. Right, so oftentimes you will look for just this first one. Right, so this represents the titration of H2SO3 with 0.1 molar sodium hydroxide. So it's still going to have a buffer region, and it's still going to have an equivalence point, right? But then it's going to go into this second buffer region over here, right? And then it's going to go up, and now I've got just excess hydroxide. Right, so it's very similar. You're just taking 2 titration curves and basically sticking them one on top of the other. Okay? I could do the same thing in the other direction. I could start off with like carbonate. Right, so here's carbonate, and I'm titrating that with a strong acid. So I'd start off with CO2, and I would convert that to HCO3 minus, and then I would add in some more of my strong acid, and I would end up with H2CO3. Right? What do I have in the solution at any given point along my titration is going to depend on how much of my titrant I added. Right? So in here, I just have the CO3 2 minus. Here, down all the way at the right past the second equivalence point, I've got just H2CO3. Technically, all along here, I've got a mixture. But by the time we're down here, right, like here, I don't have... I've got a vanishingly small amount of this. And if I'm way up here, I have a vanishingly small amount of this. What happens that's interesting is when we're in these 2 buffer zones, right? So let's look at another example. Because Ka1 and Ka2 are separated, the titration curve gives me 2 well-defined equivalence points. One is going to be here at 6, and one over here at 11.5. Right, now my second equivalence point, and notice that these are both at the same. This has got moles added instead of volume. I'm still going to have pH equals pKa at the first, halfway to the first equivalence point, but then I'm going to have pH equals pKa2 at halfway to the second equivalence point. So between equivalence point 1 and equivalence point 2, I'm going to have pH equals pKa2. Right here, right, all along here I've got a buffer that's made up of H2A and HA. Right, and so I can calculate that like I would any other buffer. And then along here, I've got a buffer that's made up between HA and A minus. And so I can do Henderson-Hasselbalch all along here, or an ice table. But if I'm doing Henderson-Hasselbalch, I'm going to use pKa2, or if I'm doing an ice table, I'm going to use Ka2 in my equation. Right, and calculate the pH all along here as a common ion problem until I reach this second equivalence point. Once I've reached the second equivalence point, this is all just excess hydroxide in solution. So along here, I've got a mixture of my singly protonated and fully deprotonated form of the acid, and along here, I've got a mixture of my fully protonated and my singly protonated form of my acid. And there are some neat mathematical tricks you can do, like what if I just have this in solution? What if I'm at my isoelectric point? Iso meaning same electric point. Right? It's just the HA point, it's in the middle. There are little mathematical tricks you can do to find these values here. We're not going to do them. We can do those in analytical chemistry. For you guys, what I want you to know is I've got more than one equivalence point. They're evenly spaced. Halfway to the first one is pKa1, and between the first one and the second one, there's pH equals pKa2, and these things stack on top of each other.